The Bolzano-Weierstrass Theorem is a pretty important theorem in real analysis. It's deceptively simple to state, but the proof is quite involved. Before we take a look at the theorem, we need to define the concept of a subsequence. So we have a sequence xn of real numbers. Let's pick a sequence n1, n2, n3, and so forth of integers with the property that n1 is smaller than n2, smaller than n3, and so forth. The sequence xnk is a subsequence of xn. Now, usually I don't write the index of interest. I drop it for readability's sake. Just write xn instead of xn, where n is the variable here that's allowed to vary from 1 to infinity. In this case, it's useful perhaps the first few times to identify specifically what the index variable is, the k. So this sequence xnk, there would be xn1, where we let k take on the first possible value, and the next one xn2, xn3, and so forth. A few things to note: nk, by definition, has to be greater than or equal to k for every k, right? This is the k, this is the nk. It's saying that n1 is the index in the first position of the subsequence. The smallest possible value it can take is 1. So n1 has to be greater than or equal to 1. You don't have a choice. But let's say that n1 was actually equal to 2 instead. It's the next one that it could be. Then every single one of the terms, even if they were exactly just 1 above here, would have to start with 2, 3, 4, 5, 6. They would all be greater than the corresponding position in the subsequence. That's going to come in handy. Sometimes I will use the notation xnk subset of xn to signify that xnk is a subsequence of xn. That's not standard notation. You might not see it in many other books or in the course notes. What a subsequence really is, if you think about it, is you had the original sequence then, and you're going to go and pick some of the elements of the sequence in order. You won't pick all of them, but you might decide to start by picking this one. This could be your first one, and first one that I picked. Then my next one could be perhaps this one. The next one could be this one. You are sampling observations of the initial sequence, respecting the order in which they appear. And you can sort of think of 2n, the set of even integers written as a sequence, to be a subsequence of the sequence n, or n written as a sequence, not as a set. Here's another example. Say that your sequence xn sequence 1 over. Here's to say 1, 1/2, 1/3, 1/4, and so forth. The sequence 1 over 2k, where k varies from 1 to infinity, going to be a sequence of harmonic numbers where you only keep even denominator. And that is a subsequence of xn. The sequence 1 over 2 to the power L, where now L is the variable that varies from 1 to infinity, 2, 1 over 4. It starts the same way, but eventually goes another way. It's also a subsequence of xn. You would write xnk from 1 to infinity is a sequence of xn. You would write that the sequence xnl, where L goes from 1 to infinity, is a subsequence of xn as well. But at the same time, xnl is a subsequence of xnk, because you can actually extract xnl from xnk by just picking the denominators that are powers of 2. But this sequence here, which I'm going to denote by yn, 1, 1/3, 1 over 2, 1 over 4, 1 over 5, 1 over 6, and so forth, is not a subsequence of xn. because the order isn't perspective. It contains exactly the same value. It has the same range of values of xn, and so in particular it's a subsequence of itself, but it's not an actual subsequence because the order here is not perspective. In this subsequence, x3 comes before x2. We can talk about subsequences even in a general sense, not based on a specific sequence. So if I have the following sequence x3n would be x3, 6, 9, so forth, is automatically going to be a subsequence of the initial one, no matter what the initial sequence was. Right? And picking members of the initial sequence and preserving their relative order. That's a subsequence. At the same time, xn is a subsequence of itself, right? This is the subsequence where I get nk equal to k. It is a subsequence. We've seen an example here previously where one sequence had a subsequence, that subsequence had a subsequence. Well, that last subsequence is not just a subsequence of the middle sequence, which happens to be a subsequence of the first, it's also directly a subsequence. Here's a theorem for us. Let's assume that xn converges to x. Of course, we don't explicitly say it here, but when we know when n goes to infinity, and that xnk is a subsequence of xn, then automatically the subsequence also converges. So if a sequence converges to some value, every subsequence of that sequence also converges to the value. How do we prove this? Well, we need to prove ultimately that the limit of the xnk's when k goes to infinity is x. We use the definition, the limit. For every epsilon, we should be able to find an integer n such that whenever k is greater than n epsilon, then xnk minus x is smaller than epsilon. This is what we want to show. Now, what do we have at our disposal? We have one of the assumptions. We know that xn converges to x. So we have that. For every epsilon greater than 0, there exists an n epsilon such that whenever n is greater than n epsilon, xn minus x is smaller than epsilon. That's not the same thing. That's the hypothesis. That's the assumption that we're making. But nk is greater than k for every k. That's because xnk, I wrote xk above here, but I really wanted to write nk here. So nk greater than k for every k because xnk is a subsequence of xn. It's one of the properties of the subsequence. So in particular, xnk minus x will be smaller than epsilon whenever nk is greater than n. So, well, that's true. I mean, that's given from the definition here. I just replaced n by nk throughout. But what I have is that if I modify this, if I say that's going to be true as well when nk is greater than or equal to k, we know this, but when k specifically is greater than n epsilon, I know that this is also valid whenever k is greater than n epsilon. I will have that nk is greater than n epsilon, meaning that because xn converges to x, this here, where I replace n by nk, is valid. And so, the conclusion is, that for every epsilon greater than 0, there exists an n epsilon, the same n epsilon as the one you had in the definition of the convergence of the original sequence, such that whenever k is greater than n epsilon, because xnk is a subsequence, nk will be greater than k, and in particular, we replace n by nk throughout, we maintain the relationship that we